Hi future GISPs. I'm going to teach you everything that I learned to easily pass the GISP exam so that you don't have to spend years reading textbooks, getting degrees, paying for prep courses, and searching the internet for information like I did. In this video, I'm going to teach you everything I learned about datums, coordinate systems, and projections. Datums, coordinate systems, and projections is the first section under the conceptual foundations category of the GISCI Geospatial for Technical Exam list of knowledge categories. Let's get started with section 101, datums, coordinate systems, and projections. A spatial reference system. A spatial reference system in GIS is a coordinate reference system. A spatial reference system, or coordinate reference system for the purposes of GIS, is a framework used to precisely measure locations on the surface of the Earth. Spatial reference systems that don't reference the surface of the Earth exist for other purposes such as gaming, but in the field of GIS, when we say spatial reference system or coordinate reference system, we are referring to a coordinate system that references locations on or near the surface of the Earth. A geoid. The Earth is not a perfect sphere. It has an uneven surface due to many forces. One reason the Earth's surface is uneven is gravity. A geoid is described in GIS literature as the shape that the surface of the oceans would take under the influence of Earth's gravitation and rotation alone, in the absence of other influences such as winds and tides. A geoid is an equipotential surface. An equipotential surface is a three-dimensional surface along which the pull of gravity is a specified constant. It's possible to create geoids because the force of gravity can be measured with gravimeters and satellites. A geoid is a measured and interpolated surface. It is not a mathematically defined shape. Geoids are used to reference heights in GIS. A spheroid. A spheroid is a sphere-like but not perfectly spherical object. A spheroid is a mathematically defined object. Different spheroids are used to represent different parts of the Earth because some spheroids fit different parts of the Earth better than others. Geocentric. Geocentric means centered on the Earth's center of mass. Geodetic. Geodetic means related to geodesy or surveying. An ellipsoid. An ellipsoid is a spheroid with a semi-minor axis in the polar direction and a semi-major axis in the equatorial direction. The equatorial radius is always greater than the polar radius on an Earth ellipsoid. Different ellipsoids fit different parts of the Earth better because the Earth's shape is not a perfect ellipsoid. There are three common spheroids used in GIS. The three common spheroids are the Clark 1866, the GRS 1980, and the WGS 1984. GRS stands for Geodetic Reference System. WGS stands for World Geodetic System. The GRS 1980 spheroid. The GRS 1980 is the preferred spheroid globally. It's used for the NAD83 and the ITRF reference frames. NAD stands for North American Datum. ITRF stands for International Terrestrial Reference Frame. The WGS 1984 spheroid. The WGS 1984 spheroid is used for the WGS 1984 reference frames. A datum. A datum is a reference surface that provides known locations to begin surveys and create maps. Parts of a datum include an ellipsoid, an origin point, a coordinate system, and a set of control points that can be used as the starting points for measurements. Datums are the basis for all geodetic survey work. Most datums used in America use benchmarks from the National Geodetic Survey. There are horizontal datums and vertical datums. Datums can be geocentric, which means Earth-centered, or linked to a location on the Earth's surface that is to be mapped. Datums are also known as reference frames or geodetic datums. A horizontal datum. A horizontal datum is a model of the Earth as a spheroid. It has two components, a reference ellipsoid and a set of survey points that establish the ellipsoid's position relative to Earth. Horizontal datums are used to assign coordinates to locations on a plane of the ellipsoid. A vertical datum. A vertical datum is a reference point for measuring elevations. It is a surface of zero elevation at which various points are referenced. A vertical datum can be gravimetric, which is based on a geoid, or geometric, which is based on an Earth ellipsoid. Modern GIS programs integrate horizontal and vertical datums seamlessly. Users don't normally have to choose horizontal and vertical datums, but a GISP should know what they are. There are three common datums. The three common datums are NAD 27, NAD 83, and WGS 84. NAD 27. NAD 27 is the North American datum of 1927. The NAD 27 datum was the first datum used in the United States. It was based off the Clark 1866 spheroid. It's based on fits from control points. It gets less accurate the further you get from Meads Ranch, Kansas. NAD 83. NAD 83 is the North American datum of 1983. The NAD 83 datum is currently used in the US. It's based on the GRS 80 spheroid. It's Earth-centered. It fits the United States well. NAVD 29. NAVD 29 is the North American vertical datum of 1929. It is survey-based. NAVD 88. NAVD 88 is the North American vertical datum of 1988. It is gravity-based. WGS 1984. WGS 1984 is a coordinate system and a geodetic datum. WGS 1984 is known for being the standard datum and coordinate system used by GPS. The difference between NAD 83 and WGS 84 locations are 1 meter or less. WGS 1984 is maintained by the National Geospatial Intelligence Agency, or NGA. A datum adjustment. Positions of all points in a reference datum are periodically repositioned in a network-wide datum adjustment. This results in a series of datums, with each datum succeeded by an improved datum. Datum shift. Datum shift is the difference in coordinates between datums caused by datum adjustment. Coordinates for locations are different in different datums or in different versions of the same datums. A geographic coordinate system. A geographic coordinate system uses latitude and longitude on a three-dimensional spherical surface to define a location on Earth. A geographic coordinate system includes a datum, an angular unit of measure, and a prime meridian. A geographic coordinate system is based on a 3D model of the Earth. Meridians. Meridians are lines of longitude. The distance between meridians decreases further away from the equator until they converge at the poles. Parallels. Parallels are lines of latitude. The distance between parallels is consistent. The circumference of lines of parallel decrease further from the equator until the circumference of lines of latitude at the poles becomes 0. A central meridian. A central meridian is the middle longitude in a geographic coordinate system. It divides the east to west extent of the mapped area in half. It is often the prime meridian, but does not have to be. The central meridian can be any line of longitude. The prime meridian. The prime meridian is a meridian that is located near Greenwich, England. It is used as the central meridian for many projections. Points east of the prime meridian have positive longitude values. Points west of the prime meridian have negative longitude values. Points south of the equator have negative latitude values. Points north of the equator have positive latitude values. The international dateline. The international dateline is located at 180 degrees longitude. It is on the opposite side of the Earth as the prime meridian. A map projection. A map projection is a transformation between angular coordinates and planar coordinates. A projection can be imagined as the surface of the Earth projected onto a surface by a light. That surface is then flattened to display the surface of the spherical Earth on a flat surface. A projected coordinate system. A projected coordinate system is used to define a location on a flat 2D plane. A 2D projected coordinate system is projected from a 3D geographic coordinate system. Components of a projected coordinate system include a projection, a datum, a central meridian, units of measure, and offsets. A developable surface. A developable surface is a surface that can be flattened to a plane without introducing distortion from compression or stretching. There will be distortion due to the projection, but not from the flattening of the developable surface. There are 3 common types of projections based on 3 common types of developable surfaces. The 3 common types of developable surfaces are planar, conic, and cylindrical. Planar projections. Planar projections project the Earth onto a flat surface that touches the globe. Planar projections are also called azimuthal or zenithal projections. Conic projections. Conic projections project the Earth onto a cone whose vertex is usually above or below one of the poles. The cone is then unrolled onto a flat surface. Conic projections preserve direction and area in limited areas. Conic projections distort distance and scale except along standard parallels. Cylindrical projections. Cylindrical projections project the Earth onto the surface of a cylinder that is then unrolled into a plane. Cylindrical projections preserve area and shape. Distance gets distorted on the upper and lower regions of the map. Meridians and parallels are straight on a cylindrical projection. Meridians are equally spaced, while parallels are not. Choosing a projection. There are some general guidelines for choosing a projection to represent different areas of the Earth, but they are just guidelines, not rules that are set in stone. The guidelines are: low latitude areas near the equator use a conical projection. Polar regions use an azimuthal planar projection. Broad east to west extents, such as the United States, use a conical projection. Broad north to south extents, such as Africa, use a transverse case cylindrical projection. Thematic mapping. If you are doing an analysis that compares different values in different locations, especially across the whole world, typically an equal area projection will be used. Tangent. A tangent projection's developable surface touches the globe's surface at one point or along one line. Secant. A secant projection's developable surface intersects the surface of the globe either at a circle of tangency for planar projections or along two lines of tangency for conic or cylindrical projections. A standard parallel. A standard parallel is a line of latitude where the developable surface touches the globe. Scale factor. Scale factor is the ratio of the map scale in a given direction. Values greater than or less than 1.0 indicate distortion. Objects appear larger than the map scale with a larger scale factor. Objects appear smaller than the map scale with a small scale factor. A standard line. A standard line is a line on a map projection along which the scale factor is 1.0. A standard line is the only place on a projection where shape and distance are truly accurate. A Cartesian coordinate system. A Cartesian coordinate system specifies locations using coordinates on a 2- or 3-dimensional plane with perpendicular plane axes. A 2D system has 2 axes. A 3D system has 3 axes. A projected coordinate system is a 2-dimensional Cartesian coordinate system. 3-dimensional Cartesian coordinate systems are used for positioning datums. A GIS displays the Earth, which is a 3-dimensional geoid, on a 2-dimensional plane with a 2-dimensional Cartesian coordinate system. Converting a geoid to a projected coordinate system is a 4-step process. The 4 steps are geoid, spheroid, geographic coordinate system, projected Cartesian coordinate system. To rephrase, the 4 steps in converting a geoid to a projected coordinate system are: first, approximate the geoid. Second, create a spheroid with an equation from approximating the geoid. Third, assign a geographic coordinate system to the spheroid. Fourth, push the geographic coordinate system through equations to a 2D projected coordinate system. There are 4 types of distortions in projections: area, shape, distance, and direction. A projection commonly used to preserve shape is the Lambert conformal conic. A projection commonly used to preserve direction is the Albers equal area projection. A projection that preserves distance is the equidistant conic. A projection that preserves direction is the transverse Mercator. There are 4 classes of map projections. The 4 classes of map projections are conformal, equivalent, equidistant, and azimuthal. Conformal projections preserve local angles. Equivalent projections preserve area. Equidistant projections preserve distance from 1 or 2 points. Azimuthal projections preserve direction and distance from the center point. Azimuthal projections are best for polar regions. Distances from the center are true in an azimuthal projection. Usually, either the north or south pole is oriented at the center of the map, giving the viewer an impression of looking up or down at the Earth in an azimuthal projection. There is a 5th type of map projection not included in the standard 4 map projection types in GIS literature. It is the compromise projection. Compromise projections do not preserve any property, but balance the 4 types of distortion. There are 4 common map projections used by mappers. The 4 common map projections are the Mercator, the Albers equal area, the Robinson, and the Lambert conformal conic. The Mercator projection is the most popular projection, and several variations of it have been developed. Four variations of the Mercator projection include the Web Mercator, the Transverse Mercator, the Universal Transverse Mercator, and the Oblique Mercator. The Mercator projection. The Mercator projection is a conformal cylindrical projection. It preserves shape and direction, but area gets distorted. It is good for mapping the equator because it has a standard line along the equator. It is used for navigation because it preserves angles. The Transverse Mercator. In a Transverse Mercator projection, the cylinder intersects the Earth along 1 or 2 lines in a north to south direction. There is a band of low distortion along the meridian. In the United States, the Transverse Mercator is used to map states that are elongated in the north to south direction. The Oblique Mercator. The Oblique Mercator is an oblique cylindrical projection. Oblique projections aren't commonly used, but a GISP should be aware that oblique projections exist. The Universal Transverse Mercator, or UTM. The Universal Transverse Mercator is a transverse Mercator projection that is divided into 60 zones that are 6 degrees wide. These zones extend to 84 degrees north and 80 degrees south. Regions south of 80 degrees and north of 84 degrees north are excluded. Distortion is below 1 in 1,000 in each zone. The point of origin for each zone is the equator and the zone's central meridian. To avoid negative coordinate values, each zone's central meridian is set to 500,000 meters, and all of the southern hemisphere zones northing at the equator is set to 10 million meters. This way, all coordinate measurements in the UTM system are always positive. UTM coordinates are written as follows. First, the zone number is written, followed by N for northern hemisphere, or S for southern hemisphere. Next, an easting value is written and the unit of measurement, such as m for meters. That's followed by E for east. After that, a northing value is written and the unit of measurement, followed by N for north. The Web Mercator. The Web Mercator is used for online apps, including Google and ArcGIS Online. The Web Mercator uses the WGS84 datum. The Albers equal area projection. The Albers equal area projection is a conical projection that preserves area. The Albers equal area projection is commonly used for thematic maps. The Robinson projection. The Robinson projection is best for mapping higher latitudes. The Robinson projection is used by National Geographic. The Lambert conformal conic projection. The Lambert conformal conic projection is used for states that are elongated in the east to west direction. It is a secant projection. It intersects the ellipsoid along two arcs, typically parallels of latitude. There is a band of low distortion between the two standard parallels. The state plane system. The state plane system consists of 125 different plane coordinate systems for the United States. Each zone has a false northing and easting applied so that the coordinates are always positive values. The state plane system is based on the transverse Mercator projection for north to south extents and the Lambert conformal conic projection for east to west extents. The state plane system uses NAD27 and NAD83 datums. The state plane system is highly accurate, with error less than 1 in 10,000. State plane coordinates are in meters or feet. Each state defines the type of foot used for their state. Each state assigns either the United States Survey foot or the International foot to their state plane coordinate system. False northings and false eastings. A false northing or false easting is a value applied to the origin point of coordinate system to change the x or y coordinate readings. It's usually used to avoid negative values in coordinates. False northings and false eastings are used in the UTM and state plane systems so that all locations have positive coordinate values. When all the coordinates in a system have positive values, it makes it easier to program, perform operations, and store data. Coordinate values are usually recorded in one of two commonly used methodologies, either degrees, minutes, seconds, initialized as DMS, or decimal degrees, initialized as DD. Degrees, minutes, seconds is a coordinate measurement system with 360 degrees around the Earth beginning at 0 at the prime meridian. 1 minute equals 1/60th of a degree. 1 second equals 1/3600th of a degree. There are 60 minutes in a degree. There are 60 seconds in a minute. Degrees, minutes, seconds can be converted to decimal degrees by dividing minutes by 60 and seconds by 3600. Those values are then added together to determine the decimal portion of the measurement. Decimal degrees coordinate measurements are an Open Geospatial Consortium, initialized as OGC, standard. In this system, a measurement consisting of a partial degree is recorded as simply a decimal number. Decimal degrees can be converted to degrees, minutes, seconds by multiplying the portion of the number after the decimal place by 60 to determine the minutes. Then multiply the remainder of the minute conversion by 60 to determine the seconds. The International Terrestrial Reference System, or IRTS. The International Terrestrial Reference System is a system of procedures for creating reference frames suitable for use with measurements on the Earth's surface. The system creates a three-dimensional coordinate system with a well-defined origin, which is the center of the mass of the Earth, and three orthogonal coordinate axes labeled X, Y, and Z. An International Terrestrial Reference Frame, initialized as ITRF. An International Terrestrial Reference Frame is a realization of the International Terrestrial Reference System. Its origin is at the center of the mass of the Earth. New ITRFs are produced every few years. There is only a few millimeters difference between the ITRF and WGS 84 reference frames. The International Earth Rotation and Reference System Service, or IERS. The International Earth Rotation and Reference System Service is the organization responsible for maintaining global time and reference frame standards. The most common reference frames. The most common reference frames in use today are the WGS 84 and the ITRF 2000. The ITRF is the international standard. The WGS 84 is the standard for the United States. A spatial reference identifier, or SRID. A spatial reference identifier is a unique identifier for a specific coordinate system. A spatial reference identifier can vary depending on the database used to store your data. The most popular spatial reference identifiers are EPSG codes. The European Petroleum Survey Group, or EPSG. The European Petroleum Survey Group created a public registry of geodetic datums, spatial reference systems, Earth ellipsoids, coordinate transformations, and related units of measurement. Most spatial reference identifier codes originated from the EPSG registry. The EPSG registry was created by a member of the European Petroleum Survey Group in 1985. In 2005, the EPSG organization was merged into the International Association of Oil and Gas Producers, or IOGP. Units used in United States coordinate systems. Units most commonly used in the United States coordinate systems are international feet, feet, and meters. A US foot equals 0.30480061 meters. An international foot equals 0.3048 meters. Over long distances, US foot measurements will be longer than international foot measurements. A grid. A grid is a set of parallel and perpendicular lines for reference as a map projection or coordinate system. On-the-fly projection. On-the-fly projection is a software technology that projects GIS datasets in multiple coordinate systems into one coordinate system automatically, without requiring manual coordinate transformations performed by the user. Now you know everything that I learned about datums, coordinate systems, and projections to easily pass the exam. Don't forget to thumbs up and subscribe to my channel so I can keep helping people pass the GISP exam and achieve the rewarding careers in GIS that they deserve. You can also find everything I learned to pass the GISP exam in my book, The Ultimate GISP Exam Study Guide, available on Amazon. My study guide is an easily understandable, comprehensive, graphical, all-in-one resource for passing the exam. You can find a link to my study guide in the description below. Thanks for joining me, and congratulations in advance on passing the GISP exam.